Hello, so we are going to give a presentation of this Harmonograph. So it's a tool, you may say it's a tool to make very nice pictures, this is the one you can see over here. But we'll explain some mathematics and the whole idea of this machinery which stands behind it. So you can get those pictures essentially as a composition of two periodic motions. One periodic motion is just one pendulum motion moving back and forth over here, and there's another pendulum-like motion moving in the perpendicular direction. Both of them are pretty boring motions, so if we just stop one pendulum and let the other go, we'll just have a straight line. Or if we have a paper moving with a constant velocity, what we shall get is a sine curve. Right? So if we let this pendulum going and we slide a paper with a constant speed, we'll get a sine function. The same will happen if we stop this pendulum and let the other going and slide the paper this way. We'll also get a sine function. But as a composition of those two, we are getting these patterns which are called Lissajous curves, and they are highly determined. They are determined only by the periods of the two pendulums. And by measuring the periods of the pendulums, we can actually exactly understand what type of pattern it is. John, would you like to take over?
In this example, the two pendulums are of approximately equal length. So when I started them going, they traced a straight line over and back, over and back, over and back. But as they fell further and further out of sync, they created more and more complex shapes, sort of wider and wider ellipses, until they come back into sync again. Start drawing straight lines over and back, which again widen. So this pattern repeats itself, and there's also an interesting self-similarity. As you look closer and closer, you see that it does the same thing again, but each time smaller than it did before. And the patterns are getting smaller because the friction in the system causes the pen to go over and back less with each step. And it's also interesting that when you make just very slight changes, you get quite big variations in the pictures. As I said, when the two pendulums are perfectly equal in length, they would just draw a straight line over and back again and again. But when there's a slight discrepancy, it creates this very interesting pattern that we see on this example. So what we're using this harmonograph to present is the fact that when you have a very complex picture like this one, if you know that it's actually determined by physical or mathematical rules, then it can be quite hard to look at the picture and figure out what the rules are. Even though in this case you can see that what's generating the picture are just two completely simple physical ideas. There could be nothing more simple scientifically than a pendulum. And when you just put two pendula together, you straight away get something much more complicated, like this. So our view of what our job is as mathematicians in the university is to try and take the complicated pictures that we see in the world, which might be pictures from biology or from physics or from economics, and try to understand what simple mathematical motions could lie behind them.
Yeah, so that's one view on it. We take a complicated picture and try to decompose it into simple explanations. You can have an artistic view on this. So combining two simple things, you may get complicated, interesting, intriguing, or even beautiful picture in place. However, this system is totally deterministic, so by knowing the periods of the pendulums, we can actually reconstruct it using simple Excel spreadsheet. So let's take a measurement, and from the basic physics we know that the period of the pendulum is proportional to the square root of the length of the pendulum.
So this one is 40 centimeters long. This one is 39.5 centimeters long. Almost equal.
So you put it all together into a computer.
Here's my computer.
So there's a spreadsheet which will be available alongside with this video. It essentially contains two sine functions with damping, and the periods of the sine function will be computed from the length of the pendulum.
So I've typed in 40 centimeters for one, 39.5 for the other, and I've got a picture that's quite different from the picture that we actually generated, even though I think my measurements were fairly exact. So I must have just made a slight error in measurement, and it's created a totally different picture. I'll just see what happens if I add half a centimeter to one of these pendula to make the gap between them a bit bigger, just an extra 5mm gap. Suddenly we're seeing something that is much more like what was created. Maybe the gap isn't quite big enough. Make the gap a little bigger, more and more structure reveals itself. This looks a lot more like the example we created. So you can see already how even just these small variations from having equal length create these quite different structures in the picture.
And there's one additional piece of information we can put into the picture. So we used this gel pen to get the structure we have over there. Now instead we can use this pen, and the fraction of the pen with the paper is much larger, so we'll get a very different structure because fraction is definitely non-linear. So let's take a look. And just to give you a comparison, we are getting a structure which I used to call the Eye of Sauron over here, while with much better pen we are getting different structure. So the fraction between the pen and the paper is also an important factor in those pictures, and will determine the outcome. So that is also something you shall be able to to observe using different inputs. Essentially, again, as we already mentioned, there are two ways to look at this experiment. From artistic point of view, we are composing two very basic motions to get something nice. From mathematical point of view, I like to look at this from the different perspectives. So we have complicated structures in the nature, and in mathematics we are essentially researching the way to realize that this is nothing more but the composition of two very simple things. So what we are doing is to provide simple explanations for complicated phenomena.